So we'll get started. Welcome to the first transportation data webinar. This is sponsored by Trek and our portal partners. The impetus behind doing these transportation data webinar series is that, as the number of data sources are increasing and there's a continuing growth of size of all these data sources, start talking about big data, we hope that this series provides an opportunity for us to discuss these issues as they come up. We will chat you a link at the end of this survey, or at the end of the webinar, and it'll be a survey, and we really appreciate it if you guys could fill out that survey so we can plan for future events that are of interest in relation to transportation data. So to kick off our first webinar, we have Dr. Kristin Tufte. She's the research assistant. She's a research assistant professor at PSU and is also the PI for the Portal project. And she will be giving us an introduction on relational databases and basic SQL querying. So, Kristin.
All right, thanks, Tammy, and thanks to everyone for being here today. Excited to get this training started. So I'm going to stop sharing my screen. I'm going to start with a land acknowledgement, and then we will dive back into the content. Okay, so I do want to start with this land acknowledgement. Portland State University is located in the heart of downtown Portland, Oregon, and Multnomah County. Today, we honor the indigenous people whose traditional and ancestral homelands we stand on. The Multnomah, Cathlamet, Clackamas, Tumwater, Waitala, bands of the Chinook, the Tualatin, Kalapoya, and many other indigenous nations on the Columbia River. It is important to acknowledge the ancestors of this place and to recognize that we are here because of the sacrifices forced upon them. In remembering these communities, we honor their legacy, their lives, and their descendants. And I acknowledge that we are not in person today, but that is the lands that Portland State is built on. Okay. All right, so back to my screen here. Okay, so this is a bit of an experiment. So Tammy has been honestly bugging me for probably a year to do a training on relational databases and SQL. So we are giving this a shot today. So I wanted to tell you a little bit about myself, and then I have some housekeeping, and then we'll dive into the content. So my name is Kristin Tufte, and I'm Assistant Professor of Research here at Portland State University. And for those of you who know it, I have managed the Portal Transportation Data Archive. So my background is that my PhD is actually in computer science and database management. And with my database hat on, I helped develop two, I guess, innovative, first of their kind data management systems, and that technology is now commonplace across many of the database vendors. And in addition to that, I've for years managed Portal, which is our regional transportation data archive, about 17 terabytes of every type of transportation data you could think of. So a lot of technical computer science database experience, and as well, a lot of experience with transportation data. So that's the knowledge and perspective that I bring here today. Few housekeeping items. We are recording this meeting, and we're going to post the recording within a couple weeks. You'll be muted and your video is off. If you have questions, I actually really enjoy and welcome questions. So if you have questions, you can either raise your hand or you can type your question in the chat box. And Tammy will be helping me manage the questions. But if you have something you're curious about or something you don't understand, please don't hesitate to ask. Finally, I want to acknowledge that this event is eligible for an 1.5 hours of continuing education credits, and it's also AICP accredited. So before we get into the content, any questions on the housekeeping or specific questions for me? Okay. All right. So this training today is based on a course that I teach at Portland State. So I teach Introduction to Databases, and I've taught it at this point kind of more times than I can count. And so what I've done for today is I've taken some key sections of that course and put them into this set of slides that we'll use today. And at the end of the training, or even if Tammy wanted to paste the link now, these slides are available to you. They're Google Slides. They're open to anyone with the link. And so what I'm trying to do today is just give you just the teeniest touch of relational databases, right? Like this is something I have spent probably 30 years of my life thinking about how databases work, how to make them function. I always tell folks, like, if you put me on a desert island with a computer and Wi-Fi, why there'd be Wi-Fi on a desert island, I don't know. But if you put me on a desert island with a computer and Wi-Fi, I could write one of these databases with the exception of this section called the query optimizer. So this is something that I have a lot of experience, both in terms of teaching and in terms of implementing this. So questions, comments, whatever you have, totally fair game. Okay, so we're gonna start. So like I said, this is about relational database management systems. And you've heard of these likely: Oracle, SQL Server, Postgres, MySQL. Many of you maybe have heard these, or some of you maybe even have used them. So I'm targeting this as really an introduction to this and not as, so really trying to just get the basics today. Relational databases invented about the 1970s at IBM's research lab. And until maybe 10 years ago, they were the gold standard for storing and managing data. So basically any data, just whatever data you had, it was in a relational databases until about 10 years ago. And 10 years ago, we got these NoSQL systems, cloud database systems, Cassandra, Mongo. Those are the names you might associate with the NoSQL systems. Those are another very legitimate form of storing data, but it's not what we're going to talk about today. So today we're going to focus on relational database management systems. Okay, so here you have a relation. It's also called a table. So in the database world, you will find that we use multiple terms for the same thing. I tend to use those terms interchangeably because that's the way it is used in the real world. So this is called a table, also called a relation, hence relational databases. So relational databases are built on relations, and this is your very first example of such a relation. You'll notice that it has columns and it has rows, and we have 6 columns and 5 rows. And this relation or table we have here is a relation that tells you about books. So It and Hamlet and A Suitable Boy are books that are represented in this table. And I really should say thank you to Deepa Varghese. She's an ex-student of mine who reworked these slides with me over the past 6-8 months. So she came up with this example, and all the graphics on the slides are due to her. Okay, so here's a relation. And this relation, this is how we store data in a database. Okay. We talk about the table structure, and there's a couple key things to the table structure. One is the name of the table. In this case, it's books. And then each of these columns has a name. Each book has an ID, it has a title, a page count, a genre, an author ID, and a publisher ID. And I want to pause at this point because it looks simple. I mean, honestly, this just looks like a table in Excel, and maybe in some ways it is, but this structure, this name, and these names of the columns is really a critical piece of relational databases. Relational databases are about structured data. NoSQL databases that I mentioned, Cassandra, Mongo, et cetera, they're more about unstructured data. But relational databases are about structured data. And what that means is that when I have a book, I know that the book has an ID. I know the book has a title. The book has a page count. I know that the book always has these 6 attributes. It doesn't have 7 attributes. It doesn't have 5. It has these 6 exact attributes. And that's really the meaning of structured data. So this is a great example of a relation. And without getting into too many details, there are certain types of data that lend themselves very well to structured data and certain types of data that don't. But the point here is that this is the structure of the relation. This is the underlying data storage format of a relational database. And what's critically important is that it has 6 attributes, and every book is always going to have those 6 attributes. Okay. So this part of the table is called the schema. So the name and these attribute names, and then 2 more things that we're going to talk about, keys and types, that forms the schema of the database. And again, the point is that this is structured data, and the schema specifies the structure of the data. And the structure is really important because you know that for every book, you're always going to have a page count. You don't have to, your system or your program doesn't have to wonder, is there a page count or not? There's always a page count. Okay, so schema is the definition of the table. And I have a bunch of little activities baked in here. So don't want you to have to spend too much time just listening to me talk. So we've got a bunch of little activities baked in here. So the first activity is create a database example. And if I clicked on this link here, it would take me to this set of activity slides. And like I said, both of these will be available to you afterwards. So this is something for you to do with pen and paper. And so your goal for the next couple minutes is to create your own database example. So pick a topic that you're interested in, basketball, students and classes. Like I said, these are slides I use for my class, and write down 2 or 3 tables that represent your topic or activity. So you want to list a table name and 3 to 4 attributes. So I showed you books, and so you could make a table about basketball teams or baseball teams or perhaps some sort of traffic data. So I'm going to pause. I'm going to give you a moment to work on that, and then I'll show you my answer when we come back. And you're certainly welcome to ask questions in chat as you wish. Okay, so quick question for you. Was that enough time, or do folks need more time? You can type in chat. oops, sorry. You can type in chat if you need more time. Okay. I think that means that Ben is good to go. Okay, thanks, Ben. Okay, so this was my answer. I like sports. And so I created 2 tables here, teams. Each team has an ID, a name, a city, and a state. And players have an ID, a name. And then this field here, plays on actually indicates which team the player plays on. So Damian Lillard, at least for the moment, plays on the Trailblazers team. Okay. Switching back to the slides here, a quick terminology, each entry in a table is called a row or a tuple. The purpose of this slide is to talk about the difference. It's just to emphasize the difference between the schema, which is the structure of the table, and the data that's in the table. So the schema specifies the structure, and the data is the contents. And over time, typically the schema stays fixed, but the data in the table changes. So here's one instance of the books table. And here's another instance of the books table, which has 2 rows have been added. The rows shown in brown there have been added, and 1 row, the 4th row, has been deleted. So this is to give you the idea the schema stays fixed and the data changes over time. Okay. All right, a database consists of 1 or more tables. So we had the books table, and now I also have 2 other tables, authors table and publishers table. And you can also note here how author ID connects a book to an author and how publisher ID connects a book to a publisher. So we know that the Joy Luck Club was written by Amy Tan. And we know that Like Water for Chocolate was published by Perfection Learning. So these are actually something called foreign keys, and it's something that's not, that I took out because I didn't feel like I had time today. So this is an example, or your first example, I guess, of a database. Okay, I guess I'm just wondering, so are there questions? I don't see questions in chat. I'm keeping an eye on that. Are there questions at this point? Comments?
This is Jody. I have a quick question.
Yeah.
If, for example, the publishers only has 1 item attached to the ID, would it be just as simple to put that item back up in the original table and not have
Yeah, absolutely. Absolutely. So this setup right here works really well if Amy Tan has written multiple books, right? And which she has. And similarly, if Putnam has published multiple books. But exactly, if you knew, and so this goes a little bit towards schema design. So if you knew that, so let's just talk about that for a second. So let me just say I was going to put the author name up here. So I was going to put Amy Tan. I was going to put an extra author column on books. And so if Amy Tan has written multiple books, then that's a concern because you have Amy Tan's name repeated multiple times, and that's not considered best practices. But in this case, like each book has 1 genre. I'm going to say that each book is going to be defined to have 1 one genre, and it's going to have one page count. So you're exactly right. In that case where you know that there's only going to be one of that attribute or one of that type of thing associated with the book, then it would be a good practice to add it as an extra column. But in this case, since Amy Tan has written multiple books, and since I want to keep track of Amy Tan and Amy Tan's age, then it's better to have it in a separate table. Is that?
Yep, that answers it for me. Thank you.
Okay. All right. Okay. Next thing I want to talk about is keys. So I said we have columns, and each of these tables also has a key. So a key is a column that uniquely identifies the rows in that table. So in this case, each book has an ID, and 5 it uniquely identifies the book, The Joy Luck Club, and 6 uniquely identifies Water for Chocolate, right? So when you create these schemas, you want to, when you create one of these tables, you're going to tell the database what the keys for the table are. And so in this case, I would tell the database that the key for books is ID, the key for authors is ID, and the key for publishers is also ID. For this type of key, you can use either an existing field that you know will be unique, or as in this case, I added this column ID, which I, as the database creator and the data creator, am going to make unique. So it's actually not really a coincidence, or it's semi-intentional that all of the key columns here are ID. So that's typically my practice when we create a table, is that I like to make a column that I, as the database maintainer and creator, control to be the ID field. Okay. So a key can consist of one column, or it can consist of multiple columns. Like I said, typically when I create stuff, we create a separate column that is controlled by our team that we can manage and we keep as unique. So actually back in the past, in Portal, we had used some columns that were, we use columns from our data providers as the keys, and I've moved away from that because we ran into trouble if the data providers changed those numbers, change those columns. So best to have a column that you control that is the key. Okay. Second thing, and let's just take a very short amount of time to do this. So think about the database that you had created before, or the table that you had created before, and what would be the keys for those tables? And does anyone did anyone create an interesting database that they wanted to share? Does anyone, I have an answer for this, but maybe somebody else has an answer of a table that they created that they'd like to share what the table is and what their key was for that table.
I'll play again, Jody.
Awesome.
I did Clark County traffic signals.
Okay, perfect.
Out with ID, but at first I wrote ATMS ID because I was going to go by the ATMS number.
Yeah.
I'm rethinking that after something you just said. Then I had a intersection name, cabinet type, controller type. Those were a few I just started on through. I was thinking about ATMS ID. That can change over time because sometimes for different reasons change that number. So I don't think I want to use that as my ID anymore.
Right. So I think that that's an interesting question for you. Do you want to use ATMS ID or not? And it sort of depends what you want, how you want to track things when that ATMS ID changes. And if the signal has I think it's a traffic signal, right? If that signal has an ATMS ID and the signal will stay the same, but the ATMS ID is going to change, then I wouldn't keep that ATMS, then I wouldn't use the ATMS ID as a key. Does that make sense? Yeah.
That's
Yeah. Okay. Okay. Any other questions? Okay. So this is my answer. And oops. So this is my answer. And the keys for this would be player ID and team ID. Okay. All right. Last section of these structure sections. So every column, in addition to having a name and in addition to declaring keys, every column has a type. So ID is an integer, title is a string, page count is an integer, genre is a string, and author ID and publish ID are integers. And this goes back to what I was saying earlier about the structure being important. So when you declare this database, you declare the columns and you declare the types of the columns. And this makes it very easy for a program to understand this data. So when a program asks for the page count of a book, your program knows that page count is an integer. And page count will never be a string. In a relational database, page count won't be a string. Page count would be an integer, assuming that you declared page count as an integer. And it may seem like not such a big difference if you're looking at the data, if you're reading the data, but from a programmatic perspective, that's a big difference. And that's also a big difference between the relational databases and these NoSQL databases. So structure of a database, we have name, we have a set of column names, we have a key column that uniquely identifies a row, and then we have a type or a domain for each of the columns.
I noticed that column names do not have any spaces. Is that critical?
For
example, page count, there's no space between the word page and count.
I have never in recent memory written a column name with a space in it. So my slides are based, the database that I use the most and I'm most familiar with is Postgres. And but all the major databases are relatively the same. I don't think you can put spaces in column names. I would have to go open a database and double check, but I don't think you can put a space in a column name.
Thank you.
Yeah. The other thing, as long as we're talking about that, Sql is case insensitive. So we're going to start to talk about queries, but you can use whatever case you want. It doesn't pay any attention to case. Okay. All right. I think I'm going to skip to get us to our first query here. So that's the structure of relations. And I'm going to start to talk about SQL. So SQL is, I think it stands for structured query language, is the official definition of SQL. And use it both to create tables and to query the database. And we're not going to talk really about creating tables much today beyond what we've already talked about. We're going to run through some relatively simple SQL queries. So SQL is used to create tables and to query the database. And to insert rows into a table. And what I was just saying a little bit earlier, SQL is a standard. So what we talk about today will be common across all relational databases. When you get to some more complicated, more advanced features, those vary system to system. So what language Oracle expects might be different from what language SQL Server expects. So when you get to the more advanced features, there's a lot of variance between the different systems, but for the basic, there is a basic standard SQL that is common across all those systems. Okay, so here's our database schema. And at the bottom here is the first simple SQL query. So this query is going to find the title and the page count of all books that have less than 300 pages. And I like short books. I don't really like long books. So hence selecting books with page count less than 300. When you look at this query, the from row here, this tells you which relation or table you're querying. So we're looking at books, and that's the name of our table. This select row says that the columns that you want to know the title and the page count. And this bottom row tells us which rows to look at. So title, this tells us which columns. And the where clause tells us which rows. And I have a little animation of this. So this where clause, the way the database figures this out is it's going to take this where clause and it's going to look at each row in the table and it's going to say yes or no. Does that row meet the where clause? So the Joy Luck Club has less than 300 pages. So does Like Water for Chocolate and Tita's Diary. And so all of those books go into our intermediate result. The next three, From Heaven Lake, Kite Runner, and The Vanishing Half, all have more than 300 pages. So they're ignored or sort of, I think of it as thrown on the ground. Now we have our intermediate answer. And now we're going to pick just the columns that are specified in the select clause. So just title and page count. And at the bottom here is the final answer, which is title. So we have 3 books, title and page count of these 3 books: Joy Luck Club, Like Water for Chocolate, and Tita's Diary. And this is the query that gets you that answer. Okay. So questions on that? I've got a couple more examples of these single table queries. And then we can talk a little bit about joins. And if we have time, we'll get to aggregates. Okay. All right, so here is another query. Select star from authors where ID equals 15. So this is the query. And again, we look at the rows 1 by 1 to see if ID is 15. What you'll notice is different about this query is this star, right? In the previous query, we had select title and page count. This query says select star from authors, and star just means I want all of the columns. So star is just shorthand for give me all the columns in the table, and the query answer is down here at the bottom right. So one author has ID 15, it's Vikram Seth, and at the bottom down here, this is our query answer. Right there. Okay. Oh, so why did the previous query need a 2-step process? So why did the query need a 2-step process? The 2-step, that's a good question. The 2-step process is really for explanatory purposes. So in reality, if this were being executed inside a database, you wouldn't actually have a 2-step process, but it was showing the 2-step process for explaining and for helping understand how the SQL query works and not it isn't actually how it would be executed underneath the hood in the database. Okay. All right, so here's another query. So this is find all books with publisher ID equals 102. And this is the result. Here's another query, and again, we're going, this is select star. And here's another query, and the question is what's different? And if you look at this, what's different is the title. And so the answer to this query will just give you the title. So select star gave you all the attributes, and title will just give you the title of books with publisher ID 102. And so I don't have the name of the publisher in this table, but whoever publisher ID 102 is, these are the two books that that publisher has published. Okay. All right, so at this point, I'm going to switch over to so I'll give you just a few minutes. And I think what Ben did was great. So when you're done writing your queries, if you could just do a thumbs up in the participants, I would appreciate it. So a few of you let me know when you're done writing, and then we can move on. So your goal for the next couple minutes is to write SQL queries to find books with more than 400 pages and find the author with ID equals 20. Okay. Right. Yes. Great. Yeah, that was a great idea. Sorry, I had to run down my, the room was getting, I had to run downstairs and turn on the air conditioning. So I'm back. Sorry about that. Yeah, I see one answer in chat. How about other folks? If you want, feel free to paste your answer in chat if you're comfortable. Okay, I see a couple folks are done. Okay. All right, I'll give you another few seconds to think about that. When, if ever, do column names or table, they never need to be quoted. You never, the only thing you quote is you would quote strings. So if I was trying to, so here's the answers. If I wanted to find an author by name, so if I wanted to say select star from authors where name well, I'll just do, so I'll do two examples here. So let me make a new slide here so that I can have larger text. Okay. Is that large enough? Can folks read that? Let me know if not. Since Adam asked the question. So if you use a string, then, so name is a string and name equals Adam, then you quote the string. Another, I don't know if I put it in slides, but another interesting way to like use strings is you can say, instead of where equal, I can say name where like, and then I put an expression here. And so this gives me, oh, this doesn't make any sense, right? I said where the book name is equal to Adam. So that doesn't make any sense, but you get the point. This query right here at the bottom, this will give you all books that begin with the letter A. So the like gives you this string, regular expression string comparison thing for those of you who know what it is. But this gives you all books that start with the letter A, and you can do other combinations in here. So it's another really good string selection query. Okay. All right. Let's do a little bit more, and then maybe we'll take a short break. I always like to take. No, SQL is not. The string is case sensitive. Yes, the string would be case sensitive. The SQL query itself is not. The SQL query itself is not case sensitive. So I always like to make that point here. Let me. There. Sorry, there. So you can type this. Right, so this right here that I'm typing is legitimate SQL. It's not. So this right here is legitimate SQL, and it will be, it's completely fine. So the SQL itself is not at all case sensitive, but yes, the string would be case sensitive. And yes, the semicolon is necessary at the end. You always have to end your queries with a semicolon. It won't execute if you don't. Okay, good. Thank you for the questions. Appreciate it. So spacing also makes it. Are the spaces between? No, you don't need a space here. You need a space between from and this. So no, the spacing. This is formatted to be easy to read. You don't need the spaces here. I mean, you do need a space between from and books because they're different words, but you wouldn't need this spacing here. Okay. We have an example useless query here. So look at this query, take a moment. This says select star from books where pub ID equals 102 and pub ID equals 103. So take a moment, think, what is this query going to return? And there's a hint, why do we call this a useless query? So I'll give you a second to think about that. So yeah, it's not actually going to return the same table. Yeah, it's the results that, I'm sorry, my slides skip around on me sometimes. The result of this query is empty. And because there's no book with publisher ID 102 and publisher ID 103. So this is in here for a couple of reasons. It's in here to make the point that, 2 points. One is that this query is always going to be empty no matter what. There's no possibility, given this particular schema and this particular structure, that a book can have 2 different publisher IDs. So no matter what, this query is always going to be empty. It doesn't matter how many rows I put in this table or what rows I put in this table, this query is going to always be empty. So that's one sort of interesting thing. Another interesting thing is, like, this is a completely valid SQL query. Doesn't make any sense. It's useless. It will never, no matter what data you give it, return a result. But it's still a valid query. And if you go to a SQL query engine and you type this in, it will happily execute the query for you. And it will happily execute this query for you. So it's just an example of example where the query doesn't make any sense, but it's completely valid SQL anyway. But the SQL, it will secretly judge you. Yeah, right? Yes, the SQL will secretly judge you, right? Okay. All right, so let's take a pause here. Let's see, it's about 2:50. And so let's just take, since this is 90 minutes, let's take a 5-minute break. Can you use an ampersand sign? No, you need to use the and. No, you can't use ampersand. You need to use the keyword and. So that's the question in chat is, can you replace and with an ampersand? No, you have to use and. Okay. So it's 2:50. So let's take a 5-minute break, and I will be back at 2:55. All right. Okay, so I'm back. Hopefully I had a chance to grab a glass of water or a cup of coffee or whatever. Let me share my screen again. Okay. All right, so we've talked about single table queries. We've talked about relation structure, and we're going to move on to queries that use 2 tables. So I will let the Trek folks answer the AICP question. So we're going to move on to 2 table queries. And there were 2 more things, 2 more sort of big types of things that I was thinking and kind of hoping to get to today. And one was 2 table queries, also known as joins. And the other was aggregates and using group by and having. And so I'm going to get through joins. I'm not sure we're going to get to aggregate and group by and having, but there are slides there, or we can do a version 2 or what have you. Anyway, so let's move on to the 2 table queries. Okay, so we talked about this a little bit before. There's select from where, and select tells you which columns you want. From tells you which table or tables you want to look at, and where tells you which rows should be kept. And I'm often asked, does it have to happen in this order? Because for people who are program and use other programming language, it's really odd that you put the tables in the middle. It would seem more natural to say, from these tables, give me these columns and these rows. But the answer is, this is the order that you have to write the queries in. Select has to go first, from second, where third, and followed by that semicolon. Okay. So here's a query that uses 2 tables. And this query is finding the name, age, and title. And so this is going to find the name, age, and title of all authors who are less than 70 years old. So finding the name, age, and title that seems pretty straightforward. We're looking at both authors A and books B. We're only interested in authors whose age is less than 70. And then there's this other clause right here that joins the two tables together. So this says that I need the author's ID to be the same as the author ID that wrote the book. So this query is going to combine the authors and books together. If we wanted to know the name, the author's name, the author's age, and the title of a book, that information isn't in one table, that information isn't in two tables. So I need to use a query like this to combine those two tables together. Okay. So the next slides after this are going to talk about what that join query is, what it really means to combine those two tables together. This slide is just a piece of useful information. And the point of this slide, there's some fancy words here, correlation name, et cetera, et cetera. The point here is just talking about the shorthand. So instead of typing author's name, authors.age, books.title, I can make a shorthand for authors, which is the letter A. So this means author's name, author's age, and the shorthand for books is B. So I put B.title here. So the question is, don't we have relationships defined in Microsoft Access so the IDs are linked and do not need to be joined? So that's something that's very specific to Microsoft Access. You don't have those relationships defined in SQL Server or in Oracle or in Postgres. In Oracle and Postgres, you do define things called foreign keys, which tell you something about those relationships, but the relationships aren't defined. So you do actually need to write the joins when you're using something like Postgres or SQL Server or Oracle. Would the query work without the correlation names? Yeah, actually, in this case, the query completely would work without the correlation names. It's a really good question. I was trying to remember to say that. So in this case, I don't actually need these correlation names. There are sort of three options for what I could write here. I could write a.name, I could write authors.name, or I could just write name. So there's 2 points here. One is that you can use these correlation names to make your life easier, so you don't have to type authors.name. Another point I want to make here is about when you need to preface a query, or when you need to preface an attribute with a table name. So let me so in this query, this is a valid query. This is absolutely a valid query. You need to preface one of these attributes with a table name when there's ambiguity. So in this case, the data books does not have a name, books does not have an age, and authors doesn't have a title. So the database can figure out that when you say name, you mean authors.name. When you say age, you mean authors.age. When you say title, you mean books.title. So if it happened to be the case that that authors had a name attribute and books had a name attribute, then you would need to say either a.name or authors.name. So the rule here is that you need to put that table name or the shortcut for the table name before the attribute name when there's ambiguity. Do we use, okay. Let me answer the second question first. Does a query run faster when you use a correlation name? No, it doesn't matter at all. So correlation names have no impact at all on the running of the query. And in fact, in general, in SQL, there's many, many different ways to write a query. So we don't quite see that here today. I could say age before name. So I could reorder some of the attributes here, but generally in SQL, you can write queries many, many different ways. And the relational database takes your query and then it does something called query optimization. So relational database takes your query, it goes and looks at it and it says, oh, I've got these 10 different ways I could make this query happen, and I'm going to pick the fastest one. So the relational database will look at your query and figure out how to make it happen. So in theory, it doesn't matter at all how you write your query, what expressions you use, what order you put things in. The database is responsible for figuring out how to make that query happen as fast as possible. In reality, when you start to use some more complex SQL, the query optimization isn't perfect, and different queries that mean the same thing, that have the same results, will run at different speeds. But in general, and in theory, which isn't perfect, but I think at a really high level, it doesn't matter at all how you write the query. The database is responsible for making it run really fast. Do we use the results of the queries to prepare for reports, or is it just for managing, manipulating the database? Both, right? This is my answer to that would be both. So you can use these queries to make updates to the database. I'm not talking about inserts or updates today, but you can use these queries to make updates to the database. But I would say the predominant use of the database is to write queries to generate a report, to generate a graphic. So for instance, the portal website runs on top of the portal database, and there's a web page, and then you tell the web page that I want to see data for I-5 for January 2nd. And then the database will turn around, the database will ask, or the website will turn around, and the website will say to the database, hey, you know what, I need data for I-5 for January 2nd. So typically there's some sort of a front end, whether it be a website, whether it be a business intelligence tool like Power BI or Tableau, or maybe it's just a textual front end. So typically that front end then will issue a query to the database, and the database will grab the data in the most efficient way possible and feed it back to the front end. So in my own experience, the website asks questions of the database, the data comes back from the database, and the website makes a pretty picture for you to look at. I also do a lot of command line querying of the database, where I just open a text interface and I type these queries into a text interface, and it gives me that data back. And then maybe I look the data myself, or maybe we create a table or a report out of it. Okay. Okay. Any other questions? Thank you for the questions. See, Tammy points out that, right, that it can be much more efficient to have your queries run by the relational database. So these relational databases have been developed for, they're 20, 30 years old. And so there's a lot of time and effort spent into making these queries run quickly. So if you're a programmer and you try to write this query, if you're a programmer and you grab the data and you try to write a program that's equivalent to this query, your program may well be much slower than running that query on the database. I have a famous example of, we had a data processing script. I think it was running on some Bluetooth data. And the script pulled the data. The script, when it ran on the raw data, not using a database, it took like 2 weeks to run, to process, like literally it ran for like 2 weeks processing about 2 weeks of data. And then when we put that script, we changed the script and we put the data in a database, it was down to like under 30 seconds. So the relation databases are pretty efficient and pretty good at executing things really quickly. So you can get a big performance improvement by putting your data in the database. There's all this overhead of setting up the schema and figuring out what the tables are. That does take time. Getting the data loading into the database, that does take time. But typically once you have the data in the database, then you get a performance win. Okay. I don't know. So was that, did that make sense? Was that clear, or other questions on that performance question or performance comment? Okay. You can maybe pick up on it. And so my work one has been managing Portal, but when I really have my computer science database hat on, what I'm really doing is trying to make these databases run as, we're trying to make them as efficient. So I'm really making databases perform really well has been a big research area for me. Okay. All right. So in the time we have left, let's try and talk about what joins are. So on this slide, I have this query that we looked at. Okay, let me answer that question. Let me try and get through joins, and then let me try and answer the question in chat. Okay, so this is a query, and this is the query I talked about before: authors and books, author name, age, and title of books written by authors under the age of 70. And this clause right here connects the two tables together. And at the top of this slide, I have authors on the left and the books table on the right. And so there's a whole series of animated slides here that is intended to show what it means to combine the two tables together in this join. And so the way this join works is it's going to pair up authors and books where the ID of the author matches the author ID of the book. So we're going to look for matches between author ID and ID. And what's shown in the next slide is how this works logically. It is not how it works in practice. So it's always almost painful for me to show these slides because it really doesn't work this way. In the implementation, it doesn't work this way, but conceptually, this is exactly how it works. Okay, so to do this query, we're going to take each row from authors and each row from books, and we're going to check, does author ID equal the author's ID? So first two rows are highlighted here. No, Khalid Hosseini did not write September Love, so we skip this pair. We go to the next pair, no match. We go to the next pair, no match. Again, no match. Now we move on to the next tuple or row in authors, and there's no matches here. Now we move on to the next tuple in authors, Langlev, and yes, there's a match. So Langlev wrote September Love, so that tuple goes in the result. And note that the result now is all the columns from authors followed by all the columns from books. So if you look down here, here's all the columns from authors, and here's all the columns from books. So we found a match, we put the tuples together, and those tuples are in the result. Not a match, not a match. And I found another match. Lang has also written Love and Misadventure, so I put another tuple in my result. No match. Yes, this matches, so it goes in the answer. No match, no match. First two fail. And now we have an interesting one. So in this case, the author ID is 22. And Paulo Coelho's author ID is 22. So there's a match between the author ID of the book and the author's ID. So that matches, but we skip this tuple. Right, exactly. We skip this tuple because we don't meet the age predicate. So Paulo Coelho, if I'm saying that right, is older than 70. And so this tuple gets skipped. And again, we skip, and now we're done. So we have three tuples in the result: September Love, Love and Misadventure, and the Nickel Boys are in our result. Now we have our intermediate result. And as before, we're going to prune out the, we're going to take out the columns that we're interested in: author name, age, and book title. And the final query result is down here. And we have one row in the final result for each time we had a match between the rows from the authors and books table. Okay, so you see the one question in chat, but any questions? Is this clear how, I've got a couple more slides that I want to cover on this to give you some more nuances of this join and a couple more nuances of SQL, but let me just pause here and see if you have questions. Okay. Okay. So here's a slightly different query. The where clause is the same, so our intermediate table is the same. What's changed is that I want name and age. And I no longer want the book title. So, right, it's a little bit silly. I wouldn't need books for this, but I want to give this as an example as to make a point. And the point is we drop title from the select clause. And so we're just going to get name and age in the result. And what's interesting here is that there's a duplicate here. So those first two rows in the result are identical. And so this is the way SQL works. SQL does not necessarily eliminate duplicates in the result. So if there's two rows that are identical, those two identical rows will show up in the result. If you want to eliminate duplicates, you can use this keyword distinct. So what's different about this slide and the previous slide is the word distinct. And when you include the word distinct, now you only get distinct rows. You don't get the duplication that we saw on the previous slide. So let me back to the previous slide. Here, without the distinct, we get duplication in the answer. And here with the distinct, there's no duplicates in the answer. So if you don't want duplicates, use the keyword distinct. If you don't use distinct, you may get duplicates in your answer. Okay. So here's another query. And so take a look at it for a second and think about what is this query ask? So just think to yourself, what is this query asking? Okay, so this query is looking for the names of authors who have written romance books and the titles of those books. And so there's 2 romance books and we want the name and title. So this query is going to give us 2 rows and 2 columns in the answer. So this is the answer. 2 rows, 2 columns. Now I have a query that's slightly different. And for those, you can think of this to yourself, or you can make a guess, type it in chat if you want. This query is slightly different. And what's different? And how many rows are going to be in the answer? And how many columns in the answer? So take a look at this, see if you spot the difference. And tell me if you've got a thought on how many rows and columns will be in the answer. And then I'll stop and I'll answer the questions. Okay, does anybody see the difference in this query and the previous one? Do I see the previous one again? Yeah, there's no join. Okay, so there's no join. So anybody got a guess as to approximately how many rows will be? There's gonna be 2 columns, right? That we know. So there's 10 rows in this answer. So what's happening is there was no join clause specified in this. And so the database is going to combine every tuple from author with every tuple from books. So it's going to go through that iteration that we saw in the animation. It's going to take every author's tuple and combine it with every book's tuple. Only it's not going to check to make sure the author ID matches the author's ID. It's just going to check if the genre is romance. So it's going to give you garbage results. Sometimes this is called a cross join. Sometimes this is useful, but most typically it's not. So in this case, it's going to give you garbage answer. It's going to give you every author paired with every romance book. So the point of this slide is pretty simple, which is don't forget to put the join clause in your query. Okay. Okay. All right. So I'm going to stop there for a moment. We're at a good stopping point. Let me look at some of these questions in chat. What if we use select distinct in the previous example? If you said select, which was the previous example? Do you remember? Do you remember which query you were asking about select distinct on? Oh, so what would happen if we use select distinct here? Is this the one? So if you do select distinct here, oh yeah, right. So your question, so the question is, what if you use select distinct on this query right here? Okay, so good question. It wouldn't change a thing. So distinct means the rows have to be distinct. Will remove rows that are complete duplicates of each other. So in this case, the name is the same in both rows, but the book is different. So both these rows stay in the result. So if I said select distinct in this query, nothing would change. You could. You also want to be a little careful. Distinct requires some extra operations. So distinct can have a performance impact because it does require, distinct requires a database to go through the duplicate elimination process, which can give you a performance hit. So be a little bit beware of distinct. You don't want it to use it when you don't need it, but when you need it, of course, it's useful, but just be aware it can have a performance hit. But yeah, in this case, it wouldn't change the result at all. How do you keep track of the variables you use? What happens if they get duplicated? Do you mean the variables like authors A and books B? Are those the variables you're talking about? Right, okay, so within the query like this, you can't duplicate them. So if I said authors A and then I said books A, I mean, it doesn't make any sense to say books A, but if I said authors A and books A, then the database would, it would give me an error. And it would say that's not allowed. So there is something which we're not talking about today, which is a subquery. And if you're using a subquery, then you can use the same variables in subqueries, and there's a whole scoping thing. But the short answer is you can't duplicate them. And if you try, you'll get an error. And related to that, when you give the database a query like this, it's going to check the query against the schema. So if I said authors, I mistyped authors, I said, and authors doesn't have a date. If I added something like this to the query, there is no relation spelled ATHRS, and so the database is going to take the query, it's going to check it against the schema, and the schema, remember, is the name of the relation and the column names and the types, and it's going to check, does your query match the schema? And if it doesn't, then it's going to give you an error. So ditto, if you try to duplicate the variable names, you're going to get an error. So it does some checking for you to make sure that you're using valid tables and that you're using valid attribute names. Okay. All right. So the very last thing that I was going to talk about that we're not going to have time for today is something called group by, aggregates and group by. So let me just go to one. Okay, let me just put this slide up. And let me just put these slides up and just mention this really quickly to you. So another really useful feature of SQL is this group by construct. So this query right here is going to find the number of books that each author wrote. So you can think of this, it's going to take books and it's going to make groups based on the author ID. So all books by the first author go here, all books by the second author go here, all book by the third author goes here, and then it's going to count the number of books in those groups. So you can say count, this is counting the number of books by each author. I could find the maximum page length of all the books by an author. So you can use count, max, min. There's a whole bunch of different average. So you can use a whole bunch of different aggregates there. There's a second construct where you do the same type of grouping, except you use having, and having allows you to pick out groups with certain characteristics. So in this case, same thing, it breaks books into groups by authors, and then it picks out the books that, or picks out the groups that have 2 or less than 2 authors. So we didn't get a chance to really go into this in depth today, but I just wanted to put it up here so that you were aware that exists. Oh, can I give okay, so let me, we want to remind, Tammy pasted a link to the survey in the chat. So I believe you'll get an email follow up with the survey also, but we'd really appreciate you filling out the survey and let us know what you think. Like I said, this was a little bit of an experiment to see if it was valuable or not. So definitely fill out the survey and let us know what you think. To answer David's question, here's, David, an example. Yeah, so you can't really use where. You can use where along with having, but you can't really use where instead of having. So where allows you to make a predicate is a fancy word, but where allows you to make a selection or a predicate on individual rows, and having allows you to make a selection or a predicate on the groups. So I can edit this slide. So this slide has a where and a group by. So this query right here, will work. And so in this query, we go through books. We find books whose title begin with the letter F. Then we group by author ID. And then we pick out the groups with count less than 2. So this will find all authors, the author IDs of authors that have written less than 2 books that begin with the letter F. So where goes first, then the grouping. So you think about it as the where is before the grouping and the having is after the grouping. Okay. All right. We are at time. So like I said, these slides, before I leave, let me do that. This is a link to the slides. I meant to do this earlier. That's a link to the slides, but you'll get an email with the link to the slides. They're available as Google Slides. Please fill out our survey. And thank you all for being here today.